models. This is three models. So large number of models, some 30 models. But these fluctuations represent different models. So different models actually give different results. But if you take an ensemble mean of all these models, it tends to show that the mean, ensemble mean of the models tend to indicate an increase in rainfall about 8 to 10% in the next 50 to 60 years. But question is, can we actually trust this? I'm going to demonstrate that we cannot trust this, and I'll tell you why we cannot trust this. And that is the problem. So even if I have an ensemble of models and ensemble mean says something, the model should be, we must have some yardstick to trust those models results. And I'm going to show towards the later part that this is not trustworthy because of two things. Firstly, this average is the standard deviation of the model to model variability is as large as the signal or larger than the signal, and therefore that is one problem. But that is not the only problem. From the physics point of view also, there are issues that I will come to. So the other burning question. So even these projections are now being revised by a new set of models. These are no new models. This is called the semi-prime model. This is where these models are going to go to the IPCC AR5 report. These models have redone all those calculations and shown that it is likely to increase. Again, the rainfall is likely to increase as an ensemble mean. But this variability from model to model remains the same. In fact, it has increased. Although these models are of higher resolution, better physics, still one model is very different from the other model, and many models have, in fact, also predicted decreasing rainfall. So again, we are left with the same issue that these projections by the models remain uncertain and remain unreliable. So these two issues are what I would like to try to understand. And to do that, of course, we have to start with, so this is the other question, that the projections by the climate models are not reliable and the uncertainty is very large, and the multi-model ensemble using say that there is some consistency about the models, that several models say that it is going to increase the rainfall because there is a comfort zone. If we say that if it is reliable, then the policymakers will be very comfortable because even though the global warming is taking place, the monsoon rainfall is going to increase. Therefore, we don't have to worry so much. But the question is very important to understand whether that is a reliable answer. What I am going to show you is that is not a reliable answer. So we cannot be in that comfort zone. We have to plan for the other possibility. In fact, I am going to show that, and I am going to argue that there is a possibility that global warming can actually decrease the rainfall. And this is something that I am going to argue during this course of lecture. So, to understand all this, we have to have a framework of monsoon. How do we understand the monsoon? And how do we sort of visualize the monsoon? What are the main drivers of the monsoon? And then, based on what kind of a framework, we can try to understand whether these results are reliable or not. So, monsoon is essentially nothing but this a northward progression of what we call a rainfall band, which is called intertropical convergence zone or tropical convergence zone. It moves with season to the land over there during summer, and then retracts back to the ocean. So there is annual variation, progression of this rain band to the north and then to the south. And this essentially produces seasonality of rainfall over this region. In some winter we are dry, and in summer when it comes over there we are very wet. So this seasonality is essentially monsoon. It is a part of an annual cycle of northward progression of what we call is the northward migrating tropical convergence zone. So with that background, if you look at the circulation of low level circulation, this is the rainfall again, and low level circulation produces this cross equatorial waves, and we have this kind of a vorticity, cyclotic vortex at the low level, and if you go to the upper level, we have a divergent circulation which produces anticyclonic vortex. So what it means is that the low level there is a convergence of moisture and produces cyclonic vorticity. In upper level there is a divergence of air which produces anticyclonic vorticity. So which means that monsoon circulation is very deep, and that if you take a cross section along this longitude and plot the vertical circulation, you can see that this vertical circulation is very deep. So monsoon is a very deep circulation, very deep system, and that is something is required to keep in mind because any theory that explains monsoon must explain that the monsoon is a deep circulation. So how the classical theory, I think all of you know that monsoon has been known as large scale sea breeze kind of a thing, because in the textbooks of geology and everywhere, meteorology, it is written that because of the land ocean contrast, land gets very heated during summer and the ocean does not heat up that fast, so therefore ocean remains cooler. So there is a low pressure over land, high pressure over ocean. So the winds blow from the ocean to the land, and due to the rotation of the earth, they form the southwesterlies. And in the winter, something exactly the reverse thing happens. The ocean do not cool down that fast. The land cools down much faster because of the low heat capacity. So it becomes low pressure, high pressure over there, low pressure over there. The winds reverse. So these essentially has been known, considered as the basic model for monsoon. But this model is wrong, because if you look at during this monsoon season, after the onset of monsoon, what happens is that this is the surface temperature over everywhere. This is India, and the surface temperature in July, for example, is older over land than in the ocean. So what happens is that after the rain takes place over the land evaporates and cools down, and then rain keeps taking place, and therefore land remains colder than the ocean. Ocean doesn't cool down that much. So therefore the surface temperature gradient, in the pre-monsoon time land is hot, the monsoon is initiated, but after the onset has taken place, the land cools down and remains cool during the monsoon season. Therefore the land surface temperature gradient remains opposite, and still monsoon remains strong. So that cannot explain the monsoon. So therefore something else has to explain the monsoon, sustenance of the monsoon. And that is essentially, instead of the surface temperature gradient, if we think about it, actually monsoon is governed by what is called meridional gradient of the tropospheric heating. It is not the surface heating. Heating in the atmosphere itself. If atmospheric heating is strong to the north, that produces a tropospheric heat source to the north, and the heat sink to the south over the ocean. These north-south differences in the tropospheric heating actually produces the monsoon winds, and that is closely related to what is called the meridional or the north-south gradient of the tropospheric temperature. Temperature not of the surface, the temperature of the air over the column. That temperature in the north and the temperature in the south are different, and these different temperatures actually drive the monsoon. And this can be shown, and I and with some of my students, we have worked on this aspect in somewhat details, and we have published several papers giving this new theory of monsoon, sort of trying to explain the monsoon in a different way. And so, in fact, the onset and this particular framework can actually define when exactly the monsoon onset will take place. The tropospheric temperature gradient changes sign at that time, and that sets in the monsoon, and then when the tropospheric temperature gradient becomes negative again, monsoon withdraws. So the onset withdrawal can be quantitatively defined if we define a monsoon as the temperature gradient between the north and the south. In fact, in reality also, although the surface is cooler, the tropospheric temperature, the average between 200 and 600 hectopascal, the temperature gradient is actually warm in the north compared to the south. And that changes sign somewhere around the onset. And then this is the rainfall evolution, and this changes of temperature gradient. For example, here you see temperature was warmer here, colder there, changes sign to this sign. That is when the onset takes place. So the onset and withdrawal can be defined as a tropospheric temperature gradient in terms of tropospheric temperature gradient, and the whole monsoon can be actually So we define this tropospheric temperature gradient as the tropospheric temperature between these two boxes, and then define the onset and the withdrawal as the changes of this tropospheric temperature gradient. And integral of this tropospheric temperature gradient in this is actually very strongly correlated with the rainfall amount in the land, and therefore the tropospheric temperature gradient actually is a very important driver for monsoon. So that with this framework, we can explain various different phenomena. For example, how El Nino affect the monsoon. Earlier, El Nino and monsoon was considered to be through the equatorial water circulation. But there is another pathway through which El Nino can affect monsoon. That pathway is through the extratropical stationary waves, and those stationary waves affect the tropospheric temperature gradient, and that affects the onset and the withdrawal, and the length of the rainy season is affected by El Nino by affecting the late onset, early withdrawal during El Nino, early onset, late withdrawal in the La Nina, and it actually affects that is how it affects the monsoon. So this tropospheric temperature gradient framework is an interesting framework to understand.